Hey everyone, welcome back. We got something pretty special today, and that is solving word problems with calculus. But before we jump into that, we have to review derivatives and differential notation. Now, someone remind me, what does this mean right here?
It's just a derivative of x squared, which is 2x.
That is just a simple 2x, yes. Now, what if I say y was some indeterminate function of x? And I say, now what is the derivative with respect to x of y squared?
That'd be 2y times dy dx.
Right. This and this don't match. You gotta do chain rule, gotta do implicit differentiation. So indeed, that is 2y times dy over dx. And likewise, if I were to just make another notational addition, let's say y equals x squared. Then another way to add on to this notation, we just say dy over dx is 2x. And likewise, if I were to say y squared was some function z, where again y is some function of x, I can do the same thing, 2y dy over dx, but equals dz over
dx.
Yes. I'm just adding something to the left side. I'm adding a left side to this.
Okay.
These expressions. Now, with this in tow, let's say z was pi times y squared. I know that seems random, but bear with me. Pi times y squared, where y was some indeterminate, or some function of x. So in this case, what is dz dx? The derivative of z with respect to x.
It'd be
You've had your fill, I feel. What is the only change I need to make to this right here? What was that?
I don't know.
This is a y squared. Z equals y squared. This is z equals pi y squared.
Yeah.
So if I take the derivative of z with respect to x, or derivative of anything with respect to a variable, does the pi affect anything?
No, it's a constant.
It just goes up front, it tags on for the right, so I have pi.
By squared over.
No, just see the pi in front of all that. It's the same thing, so say 2 pi y times dy dx, yes?
Uh-huh.
yes.
Yes. So you may say, what's the point of that? Well, what if I were to replace the z with an a, the y with an r, and the x with a t? So I'm not doing any mathematical change, I'm just making an alphabetic change. So I get a equals pi r squared, where r is a function of t. Just an alphabetic change. So instead of dz over dx, I have dA over what?
dt.
dA over dt equals, instead of 2 pi y, it is
2
Pi r.
2 pi r.
It's the circumference, right?
It is a circumference. And now instead of dy over dx, I get
r over dt.
dr over dt.
Oh,
Just a letter change. And broadly speaking, dA over dt is dA over dr times dr over dt. In this case, it boiled down to this. And over here, I want to take a little intermediate chain rule step. dz over dx equals dz over dy times dy over dx. Again, all I'm doing so far is the chain rule, and now with a little alphabetic swap, a little alphabetic shuffle.
Nice.
Now, you may think to yourself, okay, what was the point of doing that? All you're doing so far is just changing letters. Well, where have we seen this formula before?
In geometry.
In geometry, yeah. This is the area of a circle. And very special things happen if t stands for time.
uh-huh.
Okay, because now these derivatives, dr over dt and dA over dt, are what? They are rates of
Change.
They are rates of change. Yes, this is the rate of change of the radius with respect to time. This is the rate of change of the area with respect to time. So, again, special things happen when your independent variable is time. Now then, before we get to a problem, these problems are now called related rate problems. And you can kind of see why. Because I'm relating two rates.
You said they're now called related rate problems, right?
Yeah.
Okay.
So for now, we're going to talk about these word problems. They're called related rate problems.
Okay.
dr, the rate of change of the radius with respect to time, and the rate of change of the area with respect to time. They are related to each other in this equation. This equals this, so long as you stick this proportionality constant 2 pi r in front of that. Does that make sense? We've related the rates. So with this in tow, let us read off the question. A stone is dropped into a calm pond, which causes ripples to form. Ooh. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. At the instant its radius is 4 feet. At what rate is the area of the disturbed water increasing? So y'all, as it turns out, we have already laid the groundwork for this problem. We have this outer ripple, circular ripple enclosing an area. So the radius of the outer ripple is a function of time, right? This is growing with time, it's getting bigger with time. It makes an intuitive sense. And the area it encloses, since it's circular, is pi times r squared.
Right.
So r is always changing though, it's getting bigger. And if r is a function of time, what else has to be a function of time?
The area.
Yeah, area depends on time, it's a function of time. Potato, potato, tomato, tomato. But look, we've already laid the groundwork. We jumped from here into writing a chain rule expression. And this chain rule expression in particular has physical significance because these two derivatives, the first one and the last one, are rates of change. Their independent variables are time. That's that, that's that. And key point, a key point, is that this is true. This whole expression is true for any point in time. It's true when it's a small itty bitty circle. It's true when it's a big circle. It's true for any point in time. But we don't care about just any point in time for this problem, right?
No.
We care about one particular point in time, and what is describe the characteristic of this point in time for me, Mr. Jordan.
It says in quotes, at the instant when its radius is 4 feet.
Right, so we care about the instant the radius is 4 feet. And at this instant, do I know anything else? The radius is 4 feet
And the dr dt is 1 foot per second.
Is that positive 1 or negative 1?
It increases, so wouldn't it be positive?
Yes. I want you all to get in the habit, anytime we're dealing with putting a number in for a rate, get in the habit of labeling it positive or negative. If it's increasing, that is a positive 1. So this is true all the time, so if it's true all the time, it's true for this instant as well, yes?
Yes.
So, I should say true. I should say for this particular moment in time. And looks like we can go over here. Got some space to gallop. So I get dA over dt, the rate of change of the area. You tell me what I should do. I'm going to say 2 pi times...
R times dr over dt.
Yes, 2 pi times the radius at that point in time. 4 times positive 1, yes?
Yes.
So I get dA over dt is 8 pi, and finally, what are the units? If this is the rate of change of an area, how should I express that?
Feet squared per second?
Yeah, square feet per second. So at this instant, and this instant only by the way, the area is increasing at a rate of 8 pi square feet per second. That makes sense. The bigger it gets, the bigger the rate of change instantaneously is going to be for the area. Does that make sense?
Yeah.
So a broad picture though, we're relating two rates in this expression here. dr over dt and dA over dt. And broader picture, we get this from just writing a chain rule expression. So the key to doing these problems is to look at your equation, your geometric equation, or whatever equation, and then just fall into a chain rule expression. And two of them have to be rates. So let us dive into another problem. Where is my sheet? Here it is. We have ourselves a 10-foot ladder leaning against a vertical wall with its base on level ground. The base of the ladder is being pulled horizontally away from the wall at a constant rate of 0.5 feet per second. At the instant the base is 8 feet from the wall, how fast is the top of the ladder sliding down the wall? So go ahead and try this for 2 or 3 minutes and we will get right to it. Alright then muchachos, here I got a picture of what's going on. So key to these problems, you always want to draw a nice picture. Now, it doesn't have to be a work of art. It doesn't have to be on par with Da Vinci or Picasso or whoever you admire. You can if you want. It just has to be bare bone to get the point across. So here I got the ladder. It's 10 feet. Here's my x, here's my y. And I've defined x and y specifically as the distance, here's x, distance from the bottom of the wall to the base of the ladder at any point in time. That's key too. Y is defined as the distance from the top of the ladder to the bottom of the wall at any point in time. Now, someone tell me what's going on here. So first, okay, obviously I know. So let's define our knowns.
So we have a right triangle.
Good. I mean, until it falls flat on the ground.
Right.
And even it could be all the way up against the wall. But in either case, most of the time we do have a right triangle, Jordan.
Yes.
But we know for a fact that the way x and y are defined, they both depend on time, so they are functions of time, yes?
Yes.
And moreover, at any point in time, how are x and y related?
X squared plus y squared equals 10 squared.
Yes, sir-ree, and that is true at any point in time, no matter how close the ladder is to the wall, no matter how far away it is from the wall, we know that it is true.
Squared.
10 squared.
10 squared.
Yeah.
Good catch. That was good. X squared plus y squared is 10 squared. Now then, x and y are functions of time, and this is always true. So as we looked at from a previous lesson, I can take the derivative with respect to time of both sides to get a number like so. Of course, my right side is 0. This left side, though, I'm going to break it down for in this case, because this is the first time we've seen t as an independent variable. So I want to do implicit differentiation in an explicit chain rule fashion. This is the derivative of x squared with respect to t, plus the derivative of y squared with respect to t. And now, my friends, what do you notice about each pair of variables? Do they match or not?
They don't.
They don't, so we need to do what to them?
Implicit differentiation, chain rule them.
Chain rule them. So I can break this into a product of 2 derivatives. The derivative of x squared with respect to
u or
I just want them to match.
d and then x, yeah.
An x, and now times
dx dt.
precisely. Likewise, this is the same thing, just x, y instead of x. With respect to y times dy over dt equals 0. And now, you sitting silently in the corner, what are those two things? That is what? The derivative of x squared?
2x.
2x. Whereas this fella is?
2y.
2y. So look what we got here. Broad picture, we have at any point in time, just like this at any point in time, this has to be true. At any point in time, this has to be true here. 2x times dx dt, the rate of change of x,
Plus
2y times dy over dt. At any point in time, this equation has to be true.
So 2 cancels out.
Yeah, I mean, you could bring it over to the right side if you want to and can't do some cancellation, but whichever way you want to deal with it, whether it's like this or whether you rearrange it a bit, this is your general equation. This is always true. So we'll say again, for any point in time. But do we care about just any point in time for this problem?
We're trying to find a specific one.
Yeah, we want to plug in now our instant specific information. Someone tell me, what is our instant specific information?
At the instant, the base is 8 feet from the wall. So when x equals 8.
When x is equal to 8, do I have anything else I can plug in?
And dx dt is 0.5 feet per second.
Positive or negative?
Positive.
Yeah, the distance from the bottom of the ball is growing. So dx dt.
Usually, as a general rule of thumb, if it's increasing, is it always going to be positive, and if it's decreasing, is it always going to be negative?
Yeah.
And what problems?
Yeah, of course. If it's increasing, it's a positive rate of change. It's positive 5. So 8 can go in there. Dx dt can go in here. But look, I still have two variables though. I have a y and a dy over dt.
Right.
I want to solve for the dy over dt. That's the rate of change of y. But this problem doesn't give me y, does it?
No, but can't we solve it using geometry?
How so, sir?
If
How can I
x
do that?
equals 8 and x squared plus y squared equals 10 squared, then x would be, well, y would be 10 squared minus 8 squared, the square root of that.
Yes. We know that at any point in time, so don't forget about your initial information. At any point in time, x squared plus y squared has to be 10 squared. Right? So, if I care about the instant when x is 8, then when x is 8, y is 6.
Square root of 36, 6, yeah.
So, I got 3 things I can plug in. So let's see what that gives me. And now calculus is done, and it's just an algebra problem. dy over dt is going to be, I'm going to skip some steps here, negative 2 times 8 times 0.5. That's all over 2 times 6. Cancel, cancel, like you
4
Victoria said
over
over there.
6, which is 2 over 3.
So negative 2.
Negative 2/3. Does this negative make sense conceptually?
Yeah, since it's decreasing and going down.
Yeah, the rate of change of y is negative. It's getting smaller. So your answer, how fast? Well, really, how fast refers to speed. So for this particular question, you can just say, how fast is it moving down? That's just 2/3 feet every second. Does that make sense?
Yeah.
All right. Any questions? We're cool.
Well, you circled 2/3 feet. Would the answer be 2/3 feet or negative 2/3 feet?
No. Well, the rate of change of y is negative 2/3 feet per second.
Right.
But this question was asking for how fast is it moving down the wall.
Okay.
How fast is referring to speed.
Which
not
is the
velocity.
absolute value of that then?
Speed is the absolute value of the rate.
Gotcha.
So, good question. All right, well, how about we ramp up the difficulty here a bit? Same ideas, but let us move to question number 3. We have water being poured into a downward-facing conical tank as shown in the picture at a rate of 20 cubic centimeters a second. The tank has a height of 40 centimeters and the radius of its circular top is 10. I want to know how fast is the water level rising at the instant that the water is 4 centimeters deep. So go ahead and give that a go. And go ahead and look up the formula for the area, volume
Of a cone.
of a cone.
I have no idea what that is.
All right, y'all, welcome back. We have a cone on our hands. We've got a cone within a cone. We have water, conically shaped water, which I'll just say water cone. We have this water cone rising within a tank cone that's not changing. So 2 cones. Water cone, tank cone, one within the other. Now, the key for this problem is to draw a nice picture and to draw shapes within that picture. Draw geometrical shapes within that picture. So for instance, there's my center of the big circle. There's my center of the circular top of that water cone. If I were to connect them with a straight line, like so, and if I were to bring this across, like that, then what kind of triangles have I created here?
Similar triangles.
I've created similar triangles. Now, let me step back to this for a second. again, the water cone is changing. It is growing. So R is growing with time, right? As we're pouring this stuff in, it's getting bigger and bigger. H is also getting bigger and bigger. So R and H, they're functions of time. So okay, well, let's call them R and H. Whereas this and this are not changing. But no matter what point in time you're at, no matter how little your water cone is, no matter how big it is, it will always have this similar triangle relationship. Does that make sense? Okay. So, someone help me out. How can I set this up algebraically?
Like by asking us what we know already?
Yeah, how do you express similarity algebraically in this scenario?
We can say that R over H is 10 over 40.
R over H is 10 over 40. 10 over 40 is 1/4.
Fourth, yeah.
And from there you can cross multiply, right? To get
4.
4R equals H. No matter what point in time you're at, the height is always going to be 4 times the radius. Given the geometry of this tank, the tank determines this relationship. So, but again, this is just for triangles. We haven't talked about 3-dimensional stuff yet. So I need some help from a geometry aficionado in the audience.
Okay.
What is the volume of a cone? Well, I guess blue works. What is the volume of the water at any point in time? What is the volume of that water cone?
1/3 pi r squared h.
Yes, the volume of a cone is 1/3 pi r squared
H.
times h. So nice way to remember it. It's just the formula for the volume of a cylinder, and you stick a 1/3 out in front of it. That's a good way to remember it. Ooh, and again, I know r is a function of time. It's increasing with time, it's changing with time, so r is equal to r of t, and h is equal to h of t. These are my knowns. This is my starting point.
Don't we also know the rate at which the water is being poured?
We do, but we can plug that in later.
Okay.
So here, and now let's get into this problem-specific information. I know that 4r equals h. Oh, I can also say, equivalently that r is equal to h over 4. So one way to do this, I could say that v, for this problem, is 1/3 pi r squared times 4r, which comes down to 4/3 pi times what?
R cubed.
R cubed. And then from there, if I want to, I can get a chain rule expression like this. dv over dt equals dv over dr times dr over dt. So notice, the chain rule expression is pretty much identical to the area chain rule expression from the last problem. It's just, instead of an a, I got a v. Now, is this chain rule expression the best one to work with for this problem, you think? What am I trying to solve for?
We're trying to solve for how fast the water is rising, so
Right.
we're trying to find dH dt.
Yeah. So if the problem we're asking how fast is the radius changing, then yeah, our best bet would be this expression here. But it's asking me to find dH over dt, the rate of change of the height. So I don't want to work with this expression. Rather, I want to work with what?
dv over dt equals dv over dh times dh over dt.
Yeah, yes sir. dv over dh times dh over dt. So equivalently, instead of subbing in for h, I can sub in for
R.
yeah. So the volume of the water is going to be 1/3 pi. My r is h over 4.
That whole thing squared? Or
Yeah.
that whole thing cubed?
No, that whole thing squared.
Okay.
And that's times h. Yes?
Yes.
Okay. So let's see how that pops out. 1/3 times pi times a squared over 16 times h, yes? So I get pi h cubed all over 3 times 16, which is
48.
48. That is my V. Now you, help me out here. If my V is pi h cubed over 48, what is dV over dH?
Pi over 48 times 3h squared.
Exactly, pi over 48 times 3h squared. And so we get pi h
Over
squared
16.
over 16. Now Jordan, what do you think I'm going to do with that?
Well, that's dv dh, and we have a dHd. We need to solve for a dHdt.
Yeah.
We already have a dv dt though. Isn't that 40 centimeters, 40 cubic centimeters a second?
Right, so I'm going to take my chain rule expression and start plugging in my instant specific information. So this is true for any point in time. So right here, dv over dt, dealing with this guy right here, equals dv over dr dh times dh over dt. That's true for any point in time, which is also
Pi h squared over 16.
pi h squared over 16. Like this. Again, true for any point in time. Now I want to plug in my instant specific information. My hot, what do I know?
We're trying to find the instant that the water is 4 centimeters deep, so that h is 4.
So H is 4.
So
Do I know anything else?
that dv dt is 40 centimeters.
Right, I'm dumping off stuff into this tank
Right.
at a rate of 40 cubic centimeters a second, right?
Yes.
Or is it a minute? It's a minute, right?
Oh, it's 20 centimeters a second. Sorry.
20 cubic centimeters a second?
20 cubic centimeters a second. Yes.
Okay. I'll leave it, you know, for a second. So, what do I have here? 20. I
Equals.
should have been a T.
Yeah.
20 equals pi times 4 squared all over 16 times dh over dt. What do you notice happens to this expression?
4 squared is 16, and that just becomes pi.
Yeah. Cancel, cancel. So dh over dt,
It's just 20 divided
20.
by pi.
20 over pi. And final step, y'all, I want you to put units on your final answer. So if it's the rate of change to the height with respect to time, what are our units going to be?
Centimeters per second.
Right. A height divided by time is a length divided by time. So the length measurement over the time measurement. And at that instant, that is how fast this water is rising. So pretty cool, right? It's pretty powerful stuff.
Yeah.
This is stuff you couldn't do without calculus. But notice, conceptually, all we are doing is the chain rule with familiar geometric equations.
Right.
It's powerful stuff, but it's based on very simple concepts, very basic concepts. The chain rule, implicit differentiation. You gotta do some finagling here with similarity, algebraically, but other than that, it's pretty bare-boned calculus. So I want you guys to take what all you were doing in terms of calculus is the chain rule. So when you think of these problems, just think, oh, they're just chain rule word problems. Make sense?
Yeah.
So let's move on to, because I want you guys to see how this connects across classrooms.
You're doing a chemistry problem now?
Yeah, I mean, I thought about doing a physics problem, but physics is kind of cliche in its relation to calculus. Everyone kind of knows, hey, physics and calculus go hand in hand. But not many people think of chemistry and calculus going hand in hand. At least not initially. Now, if you're a chemistry major and take like physical chemistry and classes beyond that, then you'll start getting into calculus. But yeah, let's look at a chemistry problem. We have the ideal gas law. PV equals nRT. That expresses the relationship between the pressure, volume, and temperature of an ideal gas. And R there is what's called the molar gas constant. It's I'll talk about that, what it is in a second. The question here is, if we have 1 mole, i.e. n equals 1, of an ideal gas, being held in a closed container that has a volume of 30 liters, and if the temperature of the gas is being increased at a rate of 2 Kelvin per minute, how fast is the pressure increasing at that moment? So try that for a minute or two and we will get back into it. So everyone, quite a dicey problem. It's kind of unusual to see calculus in the context of chemistry, but let's take it piece by piece. If n equals 1, then I can write this equation as simply what?
PV.
PV equals I times T.
Yeah, PV equals R times T. Now I promised you I would explain what R is. R, again, is what's called a molar gas constant. And R is has a value, I should say that, of 8.314 approximately. Has units of kilopascals, that's the measurement of pressure, times liters over Kelvin. So a pressure measurement, that's the volume measurement, that's the temperature measurement. That's the units for this molar gas constant. It's a constant, it's always this much. Now, the third piece, the last piece we need is that the container that's housing the gas is closed. And the gas is occupying this container, but it's always closed. So no matter how hot that gas is, no matter what pressure that gas has, it doesn't matter in terms of volume. The volume is still always
Constant.
Yeah.
It's always going to be 30.
Yeah, it's always constant. Volume of the gas. Always a constant, 30 liters. So, with this stuff in tow, that V is constant and R is constant. Let us take the derivative with respect to time of both sides. What can I do to this left side?
You can take the V out because it's constant.
Yeah, constants can just be pulled out front and they go along for the right. So V times derivative P with respect to time has to equal what here on the right side?
Well, R is constant, so you can take the Y out too, right?
Yeah, just I can do what I did with V and also pull the R up. That's going to be R here times the derivative of temperature with respect to time.
Okay.
So pressure's changing, temperature changing, but R and V are remaining the same.
Nice.
Now, which of these two rates, rate of change of pressure or rate of change of temperature, am I trying to solve for?
You're trying to solve for the rate of change of pressure.
Yes. And to do that, all I have to do is do what to both sides?
Divide both sides by V.
Precisely. The rate of change of the pressure is going to be R times the rate of change of temperature divided by V. And now it's a simple matter of plugging in my values. R is 8.314. V is 30 liters. And what's the rate of change of temperature? Please remind me.
Positive 2 Kelvin per minute.
Positive 2 Kelvin per minute?
Yeah.
Okay. So when you do that, so run that in your calculator.
Okay.
Help me out.
It would be 0.554 kilopascals per minute.
Yeah. 0.554. Again, it's pressure divided by time. So the pressure measurement, in this case kilopascals, divided by the time measurement. In this case, the problem gives you that in minutes. So at that instant in time, this is how fast the pressure is increasing. So again, calculus, the applications are infinitely broad. There's applications in physics and chemistry. And a question like this is something you couldn't do in a regular non-calculus chemistry course. Now in later science courses, you'll have questions like this. But yeah, that just goes to show you that calculus is very versatile. Any questions? We're good?
Yeah.
Cool.
Hey, if you're gonna wear a shirt like that, you need you. Hey, if you're gonna wear a shirt like that, then you're gonna need to do something to deserve it. You need to show something heroic.
But I'm not sure how heroic I can be. I've lost a lot of muscle since this quarantine has started.
Well, why don't you summon hope? I want to see some push-ups, hope. Handstand push-ups. Give me 10. 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One more push-up. One more handstand push-up. One more. Last one. Show you're a hero. Do it. Do it. 10, 10, 10, 11. Cookie attack. Go get him. Go get him.